Um, this video is going to be on Bayesian estimation, which you can kind of think of it as an extension of maximum likelihood estimation. So I want to clear a little something up with max likelihood estimation. We said our likelihood function was basically this PDF, this joint PDF. What is a PDF? Given an argument, kind of the likelihood of an outcome for any given argument. So what argument maximizes the likelihood? It's the argument where the peak of the PDF is. Call it the mode. It is the mode. So in effect, we were finding that when we did maximum likelihood estimation, we were in effect finding the mode of a joint PDF. So now let's go to Bayes. Remember Bayes' rule, PDF of an X conditioned on a Y. Look at it, well, it had this a priori PDF of X before you knew about it. So you went from what is the PDF of X before we got a Y to what is the PDF of X given that we have a Y. Went from a before and an after. So you can call that a sort of a priori PDF and an a posteriori PDF. And we'll replace this denominator here. This integrand here, trust me, is the joint PDF of X and Y. This was another way to write that, if you recall. And if you integrate the X out of the joint PDF, you just get F of Y. So we'll replace this F of Y with that integral. Now let's see. Theta now is going to play this role of X up here. And this big X or chi here is going to play these roles of Y up here. And that is the outcome of K experiments, like we did with maximum likelihood. So we have this formula for this PDF, this joint PDF. So we want the theta that maximizes. We want the mode of that thing. So we want the theta that maximizes that, which means maximize this. And this denominator here is just the same. All the theta gets integrated out of it, so it doesn't show up when you try to maximize it. So if we just maximize the numerator, we maximize this. So here's the new thing we want to maximize for Bayes estimation. If you look at it, for maximum likelihood, just this part, just this conditional part was what we maximized. Now we multiply it by the a priori PDF of what we're trying to estimate. And that's the new thing we maximize. By the way, if your a priori is total uncertainty, which would mean a uniform distribution, the Bayes estimate, same as the maximum likelihood estimate. Sometimes I'll call it Bayes, sometimes I'll call it maximum a posteriori or MAP. So let's do that flip coin thing again. When we just did MLE, in general, it was just the number of heads over the total number of flips. It's a flip, okay? Not a head, not a coin. For maximum a posteriori map, it's not only the same thing we had from MLE, we tack on this a priori. So here's the thing we want to maximize. What is the a priori? Well, somebody has to tell us that. And for this example, we'll say it's this. So the a priori looks like this. It's a legitimate PDF. It integrates to one, okay? So the thing we want to maximize then is this. You know, here's what we maximized for just MLE. Take my word for that from previous. So there's that plus this a priori PDF, which is that part. Algebraically simplify and you get this. Now use simple scalar calculus, take the derivative, set it to 0. You get this. It's the number of heads plus 1 over the total number of flips plus 2. Compare it to this. If you didn't do any flips, for MLE, you had 0 over 0, undefined. For map, you have 1 over 2, which simply maximizes the a priori PDF. So you could say it has that advantage. Let me just say a couple things about that. I did an actual couple of experiments with a real tack. Let's see, one of these is MLE and one of these is map. MLE, I guess in this experiment, we started the first toss was a tail. So it started out with, and it estimates that theta is 0. Then it must have got ahead. It went back up to 50-50, some more tails and more heads. And then, and on the other hand, the map started out, it got ahead, but it didn't deviate as far from 50-50, which was kind of its a priori estimate. If you had the 0th toss here, MLE would be right here at 50-50, and it goes down because we got a tail. In this other experiment, the first 2 flips were heads. So MLE started way up here at 100%. Map went from 50 up to here, and then up to here, and then we started getting. But you'll notice after a few flips, they both are about the same. The more flips you go, the more they get similar. They only deviate by very much in the very early flips. This is actually a cause of some controversy within the estimation and probability community. Bayes' rule is solid probability. Bayes' estimation is controversial because where did you get the a priori from? Don't do any experiments. What data are you using to come up with the a priori? We're getting into a little bit of a philosophical argument. I'm not going to go there, but I'll just say there is that controversy. So let me do another example of Bayesian estimation or map estimation. We did the Poisson with MLE. Here was the Poisson distribution. So the MLE part, the joint PDF we did was this product of individual PDFs. But now we need to tack on this a priori. And we'll just say somebody gave us this. So we have this product, things that look like this, times this other PDF, this lone guy out here. So our log likelihood function, you could call it, well, still a map thing, or the thing we want to maximize is this J, which is we'll call it the log of this whole product, which will be this sum due to these guys plus the log of this guy. And a common mistake many students made was they would put this guy in with the sum. No, he's not like these other guys. He's outside the sum. Well, he's part of the total sum, but all these guys are alike. So when you sum over guys that look alike, this guy's not going to be in there. So this part's the same as MLE. This part is the extra part due to the a priori. And from there, we take the derivative of the whole thing, which will be the derivative like we did with MLE, minus 1. Now we're back to set it to 0 and do some algebra. Here the result, you get a 1 over k plus 1. MLE, we just got a 1 over k. In effect, well, the answer was simply the sample mean of x. Now that's not the case. This is not the sample mean of x anymore. Anyway, that's how maximum a posteriori or Bayesian estimation, at least in those kind of simple application problems.